that were very intuitive and make sense, like the divergence has to do with blowing up of the field, and the curl has to do with a circulation around some point where there's the curl is not zero. Okay, but that is for you. That was to understand. But eventually, we proved that the divergence could be written in this form, and the curl could be written in this form. Okay, so those are practical things that we didn't use to define, but we proved them that they are true given the intuition that we built at the very beginning. Then there was one important, the divergence theorem that we proved last class. That was almost a direct consequence of the definition, the microscopic definition that we introduced. And it's that given a vector field, then we have this. So if you remember, at the very beginning, so just to remember how is that we did this, at the very beginning when we defined the divergence, we just used divergence of f, and we defined it as the integral of f dot ds divided by the small volume. Remember, that was the original definition. And then we proved this result simply by looking at a volume and dividing the volume in little three-dimensional pixels, and realizing that all the surface terms canceled out in this integral, but the volume terms added up, and then we only ended with terms on the surface. Okay, so I mean, it's been almost a month, so hopefully you remember what I'm talking about, but those of you that do good, those of you that don't, at least go back to your notes, okay, to understand, because familiarity with these concepts will be very, very important very soon, okay? Whatever, okay? So as a recipe, which I don't like, but we have this theorem that we proved. And the way it works is that we have volume with a boundary S, and to emphasize in this case, since we have a volume, the surface S needs to be closed, so we just remind ourselves by writing that circle, and this is the geometry that makes that statement correct. Okay. So then, last class, and just for the sake of time, so we move on a little bit more. There is another very important theorem, which is you heard, you've seen it, many of you have at least, the Stokes theorem. Okay. So that one on top is due to Gauss, so it should be called Gauss theorem, but I guess that Gauss has a lot of stuff on him, so Stokes doesn't have that much, so we can, yeah. So, no, he still, he did a lot of stuff anyways, but, so, all right, so I'm not going to, last class what we did is we proved this, if you remember. Okay, starting from the definition of, and there was an issue with the sign that, right? That was a minus, but you don't remember?
I wasn't there.
Oh, you were not there. That's right. But you saw the video, I hope.
Yeah.
Okay. Anyway, so put it as an exercise to figure out the right sign. Okay, but we proved this thing from the definition of the curl, that for sure, okay? What I didn't do is to prove Stokes' theorem, and I will just write that as an exercise in Canvas, because it's good practice, and it's very similar idea as the divergence theorem. In the divergence theorem, we divide a volume into many little volumes, and then we get the surface term. In the case of Stokes' theorem, the statement is like this. Oh, by the way, before I forget, I meant to say something. This term here on the left remember, it's important, is called the flux of the field F. Okay, and for obvious reasons, we spent a little bit of time on that before. Flux means how much stuff goes through a certain membrane, through a certain surface. In this particular case, the surface happens to be closed, but the flux is defined also for open surfaces anyways, okay? Like that example that I gave you of a net with fish going through, okay? That would be the flux of fish through the net, okay? Fine, so in the case of Stokes' theorem, we can follow a similar line of ideas and prove this. Let me write it like this for now on. Okay, so I'll explain the notation, and this guy can be like that, and this, okay. Okay, so the notation I'm using here is that this vector dl is a line element, is a vector. So the picture that goes together with that result is like this. You have a curve, C, in space, okay, like that. And then S in this theorem is an open surface. It has to be, sure. Okay, so this is in contrast with what we had in the divergence theorem. In this case, the surface is open, and that surface is such that has C as a boundary. Okay, so for example, if you have this bottle, okay, so the surface is the surface of the bottle, and the curve, for example, is this circle on top. Clear? All right, so it's very clear from this description that given a curve C in space, there are infinite surfaces S that have the same boundary C. Correct? That is not true in the previous case. Given a closed surface, there is only one volume inside. Okay, but in this case, because the surface S and the curve C is a one-dimensional object and a two-dimensional object living in 3 dimensions, there is more freedom. The other things, the volume is already 3-dimensional, so there is only one possibility in that case. But given that you have low-dimensional objects living in 3 dimensions, then there is more freedom to adjust more things in there. Okay, that's the reason why, given C fixed, there are many S's that are possible. So for example, if the curve C dimensional curve, because not all curves are 2-dimensional, right? You can imagine that they can actually, you need 3 dimensions necessarily. There are things that you cannot put flat on a table, right? But if you could put that curve C flat on a table, meaning that it's a planar curve, then in that case one of the surfaces S is the plane itself, the inside part of the plane itself, right? And then there are others that are in 3 dimensions. Okay, so let me see.
C doesn't have to be in 2 dimensions?
No, it doesn't have to be. C is any curve in 3D. It could be, of course, 2-dimensional, but doesn't have to be. So Yeah. So just as a quick refresher, so remember that we started last class from the definition of the curl of f, which eventually at the end of last class, after some work, we proved that it's equal to this thing. So we started by using the definition okay? So this was the definition. So if I concentrate on that definition and I take a curve C and a surface S, I want to prove that. That's what I'm going to post for you to do, okay? The hint is the following. It's just to simplify a little bit. If you remember the way we proved the divergence theorem, we can follow similar arguments here, okay? The details are different, but the idea is the same. So what you do is you take this surface S and divide it in pixels, okay? So it's going to look like this. So this is the front, and of course there are going to be lines that end at the back part of the curve C, and similar, there are some lines like that. Okay, so what we need to do is to go to one of those little rectangles. You can consider it a square if you want, it doesn't matter because you can do that if you want. Okay, and so this is the hint for the proof. And then once you go there, and let's say that you choose the distances such that it's a square, just to simplify your life, because you don't need to make it complicated, then this little square is going to have a side A and A, both of them small. Okay? So if you stand on that square and look down, then basically you're going to see a little square, okay, from the top. So it's going to look like this. Okay, and so locally now, just to simplify the analysis, you can say, okay, since I'm here, I can do the analysis of, I can use the definition and see if that thing works on this object, on this small object. Okay, so now, all right, so I can take a local system of coordinates to simplify my life, and I say, why not? This is going to be my x-axis locally, and this is going to be my y-axis locally, and z pointing out. Okay? I can go to any of those squares and do that analysis. I'm going to just concentrate on one of them. Okay, and so the Stokes theorem requires that I take the curl and do a dot into S, correct? Now here it's not very clear the direction of this thing S, because if you remember from before, the ds vector is a vector of magnitude, the patch of area, but the direction is the direction of the normal pointing out, correct? Okay. But it's not very clear what does it mean to point out when I have a flat surface, correct? So that's a little detail that only will affect your sign when you prove, but the answer to that is that to figure out which way the normal points and also which way the ds points, you need to look at the global picture of the system, meaning you need to go back to this picture. And the way the theorem works, that's something I need to tell you because that's part of the proof that we need to do, is that in this case the surface S is open, so it's not that clear because I told you before that when it's enclosed, then the normal by definition we are going to use the standard that points out. But what if it's open? Okay, if it's open and we are dealing with Stokes theorem, what what you can prove, and you will prove, is the following. That I'm not so sure how you are looking at this picture, but after I drew this sort of meridian lines, it should be clear, but let me just emphasize. So for that curve C, this part over here is the front. And then that other part is the back. Okay, this is important for what I'm going to say. So then if I walk, let's say up front, I walk from left to right, like that, then in the back, I'm gonna walk from right to left, correct? I want everybody to see that. Okay, so it depends on how you look at the picture, but that's what I want. So up front, I walk from left to right, and in the back from right to left. So in doing that, I sort of generate an orientation. You can think of a clock that way, okay? And in that particular case, if I look from the top, the clock is moving counterclockwise. Okay? All right. So then, in that case, if I circulate like that, you will take the normal, the local normals outward this way, mostly pointing in the direction of my right hand. Remember from freshman physics? Okay, so I look at the direction of motion and take my 4 fingers in that direction, and then where my thumb points, it will tell me roughly which way the normal should go. Okay, because at this point I have 2, normals. If I were circulating the other way, then the normal would have to point down for this to be true. Okay? This is very important because the S could be something or the negative, and both are correct. But if I follow the rule I just told you, the theorem is correct. Okay? That's something you need to think about that when you prove it. So the point then is that when I go back to this little patch that is flat, whether the ds will point up or down depends on where I took it from. Okay, so if I look at this picture here and I decide that my x is here and my y is here, then clearly, according to that picture, the ds is going to be in the z direction. Okay, but you need to refer to the global picture to be able to tell that. Okay, so then I take